All right, hello and welcome. My name is Stephanie Hendrickson. I'm executive editor for Additive Manufacturing Media. Pleased to be moderating today's webinar brought to you by Mantle. So today we're going to be learning about the company's metal 3D printing technology for producing injection molds and how rapid tooling made this way can dramatically accelerate product development. This presentation is going to include some real-world case studies where manufacturers shortened product development cycles by as much as 80%. Our speaker today is Ethan Rido. Ethan is Director of Marketing at Mantle, and he has extensive experience in technical marketing for design and manufacturing products. He's previously worked at Desktop Metal and with the rapid prototyping team at MIT Lincoln Laboratory. Before we get started, just two quick housekeeping notes. First of all, you should see a tab on the right side of your screen, a panel on the right side of your screen with the Q&A tab. If you have questions for Ethan at any time during this presentation, please submit them through that form and we'll leave time to answer as many as we can at the end. And secondly, I do want to let you know that this webinar is being recorded. So if you're not able to stay for the whole thing, if you'd like to refer back to it later, if you'd like to share it with a coworker or a colleague, that recording will be available usually within 24 hours. You'll get that in your email. So all that being said, I'm going to head backstage until the Q&A, and I'm going to turn things over to Ethan.
Awesome. Thanks for the introduction, Stephanie, and hello, everyone. Thanks for joining me today. My name is Ethan Rido, and today we're going to be talking about accelerating product development, specifically with rapid tooling. I'm talking a lot about how to bring plastic parts to market and what that process looks like, some of the challenges, some of the advantages, and some of the different ways that people are doing that. A quick agenda for today, and again, feel free to ask any questions throughout. I'm happy to answer any questions that come up. We're going to quickly look at the product development process to understand the different stages, the different processes. We're going to look at a couple of different common methods of how plastic parts are prototyped today, look at the pros and cons of those. We're going to specifically talk about how rapid tooling is used during product development and allows it to be dramatically accelerated during that prototyping stage and bridging stage. Then I have a bunch of examples. I have some parts here on my desk that we'll talk about of people who are actually doing this and how they're using rapid tooling to dramatically accelerate their product development. And we'll look at a ton of examples of that. And without further ado, let's go ahead and get started and jumping right into it here. When we look at the product development process, specifically for plastic parts, for medical components, for aerospace, automotive components, for these highly regulated industries specifically, and really in general, the product development process, we see that it's incredibly fast in the early stages, in the early design stages. You're working in CAD, maybe in some simulation and some assemblies. You're understanding how your parts are going to fit together. You're going from a sketch to maybe a 3D rendering to understand what is this part going to do? Is it going to function, etc. Of course, early on, there's some great plastic 3D printing opportunities where we're printing form and fit prototypes, just something to understand, does this design work? How does it feel in my hand? Is it going to fit together to understand, how this design works and iterate on that very, very quickly? What we see really, really slow down the product development process is when we move into actual design verification. Because unfortunately, a plastic prototype, a CAD model is only going to get you so far. Eventually, you're going to need to move into an end-use material. For most plastics, that's an injection molded polymer that's going to perform very, very differently than a plastic 3D printed part. And you don't just need to now validate the design of the part itself, but now we need to start to de-risk the actual manufacturing process as well, the production process. We have to understand, can my part be made in volume for an affordable price via molding, via other processes? And that's where we really see the product development process kind of grind to a halt. And what is one of the big reasons for that is because generally you need tooling at this stage. And tooling is often known to be some of the most expensive and most time-consuming things to produce. So we really see that need for tooling, which is super essential to validate both the functional design as well as the manufacturing process, but really, really starts to slow things down. So if we start to kind of break this out a little bit, like we just talked about, in the beginning, you're going through these design phases. This is happening really, really rapidly. You're working in days, weeks, months, years, depending on how many iterations you're going to go through. But luckily, with modern CAD and modern plastic 3D printing technologies, you can go through design phases in hours. Very, very fast. But unfortunately, the materials you're printing are pretty terrible material representations compared to a production material that's going to come out of a mold or be produced in volume. So while you're learning a lot about the form and fit of the part, you're not really learning anything about the function of the component. It's almost impossible to use this for your design verification to understand if this part's truly going to work in volume. And of course, you're doing nothing to validate the actual manufacturing process, which is a whole nother step of this process. Once you finally have gone through this, and this is a great process, and I'm sure we could spend a whole webinar just talking about different advantages and disadvantages of this. But once you have a design that you want to go forward with, now we need to validate the design itself in a production environment, which means I need to get a part in an end use material. There's a couple different ways we see our customers doing that. The first would be machining. You can machine a plastic component, of course. You can machine something out of ABS or out of polymers or glass filled or nylon or whatever your end use molded material is going to be. You can go ahead and machine a part out of that. What's the advantage of that? It's very fast, right? You're not having to wait for that tool. So you're going to get an end use part in your plastic component without having to wait for a tool. Unfortunately, it's not a perfect material representation because it wasn't produced with the production manufacturing process. We see this especially be true for things that are glass filled or filled resins, where you're actually cutting those fibers during the machining process, and that ends up causing the part to perform quite differently than it would in a production environment. Depending on the application, it's not always usable for design verification, and you're doing nothing here to validate the actual process. Another option here is to use a prototype tool. And we'll talk a little bit about prototype tooling in a second, something like an aluminum tool or even some plastic 3D printed tools. While this is a little bit slower, it's a much better material representation than a machining process because you're actually flowing plastic, you're flowing resin, and you're understanding how that part's going to perform as an injection molded part. Often it's not usable for design verification or process verification because it's still very, very different than what's going to happen in production. Another option is to use a prototyping service. We see this quite often, something like Protolabs or Xometry or these other great prototyping services. Very, very fast. They're going to get you a good material representation because you're getting an actual molded part. But again, you're not learning much about the actual end use manufacturing process because you're molding in an aluminum tool, which has some challenges that we're going to discuss in just a moment here. And of course, you're not learning too much about the actual tool design itself because you're not actually seeing and producing that tool. Once you have gone through that step, which these are the three most common ones we see our customers using to do that design verification and validation, now we need to move on to process validation. And that means we need to actually validate our part in production before we're going to go and make a million of these. We need to make 1,000 in a production tool to understand, is it still performing the same as it did in our prototyping process as it is in production with the steel tool. Here we're seeing, a perfect material representation. It's perfect for a design verification, and you're also validating your process. But of course, it's super slow. If you know anything about production tooling and steel tooling, it's often some of the most time-consuming and expensive parts to make across any industry. So getting to this stage is where things, you go from days to weeks to often months, if not longer here. I just quickly want to share a little bit more about aluminum tooling and some education here. Aluminum tooling, we get kind of great feedback for the right applications. If you know anything about aluminum or soft tooling, it's often called, it's really fast compared to a tool steel tool. And the reason for that is because it's very easy to machine since the hardness is low and it's a relatively soft material. Aluminum is relatively inexpensive, both the raw material as well as the process because of that low hardness, which makes it easy to produce. And another benefit here is it actually has quite great heat conductivity. So we see a lot of aluminum tooling in packaging and thermoforming applications where the volume is really high and it's not overly abrasive because you can cycle it so quickly because of that awesome heat conductivity. The cons here, lower durability thanks to that hardness, the lower hardness and the fact that it's a soft material, so it's not going to last a long time. Sometimes that's totally fine if it's just a prototyping application, or maybe it's a few thousand, or it's not a very abrasive resin, that can be okay. One of our benefits is also a con, which is that great heat conductivity. This can lead to a lot of challenges when moving into production. We hear from customers all the time that their part was working awesome in an aluminum tool, and then they move to a steel tool and they're like, it's warping, the tolerances are all off because the shrink rates are totally different now because the steel is conducting heat so much differently than the aluminum tool was. Harder to repair, which may not be a big deal if you're just doing a prototyping application here, and then lower dimensional stability because of those thermal properties again. It's got a higher coefficient of thermal expansion, which means the tool is going to move a little bit more on you during processing as well as during molding applications, which means it can be a little bit harder to hold really tight tolerances. Just wanted to share a little bit more detail about aluminum tools because now we're going to start to talk about, what if we could remove aluminum tools from the equation? What if we could remove that machining step and go right to this idea of going straight from plastic 3D printing to a steel tool? Wouldn't that be awesome? Why don't we just do that? And of course, it's because of the very, very high costs and the very, very long lead times associated with steel tooling. But wouldn't it be awesome if we could use a steel tool to get our end use plastic material as well as our end use manufacturing process to allow us to get true production parts during prototyping? That would enable steel tooling for part verification and trials. It allows us to validate that manufacturing process and mold functionality, which actually allows us to start to learn about our molding process as well, the pressures, the temperatures, all of that, to actually understand how our parts are going to perform in production. That steel tool could then be used to bridge or in production and ultimately just de-risk production. So if all of these things are so great, why wouldn't everyone just be using steel tooling early in development? Why would we bother with aluminum tooling and machining and all these other processes? I think you know that, and it's because there's a lot of challenges associated with steel tooling, as I've mentioned. Really, really long lead times and high costs due to the extremely precise tolerances we often see, strict surface finish requirements, and that these tools often have to be very, very smooth and have excellent surface finish requirements, which can be challenging, especially when working with a mold component. Specific, hard to work with steels. These are very, very specific materials that have high hardness, which makes them very hard to work with. And that really limits this new product development speed and by using these steel tools. That's where I'm going to kind of introduce Mantle. And for the right applications, we actually see our customers doing this, where they're moving right from a plastic 3D printed prototype straight into a Mantle tool, which is tool steel. So we're often seeing, a lot of our customers are saying they're getting production tools and prototype timing, where now we're using a tool steel tool to do that functional and process validation. And you're really validating the entire manufacturing process right after you move on from a design freeze. It's fast. It's similar to prototype costing. You're getting that perfect material representation, meaning the material that's coming out of this tool is identical to what's going to be done in production, which is not the case for a machine component, a plastic 3D printing component, or a aluminum tool component, where it's going to be different than what's going to be happening in production. It's going to be usable for verification and, of course, to validate processes. And, of course, all of this is happening in dramatically less time, which enables you to bring products to market faster. We're going to move over now, kind of talk about how this is being done. In that, in the conventional toolmaking process, there's a lot of steps involved. Everything from quoting the tool to sourcing the raw materials, to doing the CAM programming for the rough milling step, the fixturing of the component. Often there's heat treatment involved to raise the hardness even higher after a rough milling is done. Then there would be a hard milling step after heat treatment to hone in those tolerances even more. And then if you're familiar with EDM, we're going to talk a lot about sinker EDM today, because molds often require a lot of sinker EDM steps, which are extremely time consuming and expensive. So the way that Mantle accelerates this product development, reduces cost, reduces lead time, is that it cuts out almost all of the most expensive and time consuming steps of a tool build. We're going directly from the Mantle process to something like this. Our customers are often telling us that Mantle gets them 85, 75, 85% of the way there, and all that's required is a little bit of finishing. Generally, that means grinding to the exterior and finishing of ejector pins to just kind of hone in those last little bits, but we're removing all of that milling, all of that hard milling, all of that sinker EDM process to allow you to get something that's almost complete, just requires a little bit of finishing. So removing those really, really expensive and time-consuming steps of the tool build. Let's talk about how this actually works, because it's a little bit of a unique process and a little bit different than many other additive manufacturing processes. But Mantle's tool-making technology combines two different pieces of equipment. There's a printer, which you're seeing on the left, and questionable whether we should call it a printer or not, because once you learn how it works, you'll see that this is a little bit unique. And then a furnace, which is on the right. There's three main steps involved in the tool-making process. There's printing and shaping, and we'll look at how that actually works. And then there's the sintering step, which is where we're actually hardening the material. So first, the part goes through the printer, and then it goes into the furnace to be hardened. One thing that's a little unique about Mantle, especially compared to other metal 3D printing technologies and technologies in general, is that we actually start by printing a metal paste. That paste is very similar to a toothpaste. It's metal particles of various different particle sizes mixed with some solvent and some binder as well. And that's what you're seeing here on the right. Is you can see it's this kind of concoction of paste, which is a combination of metal powder, binder, and solvent. The reason that we're using these three materials is that the solvent allows the paste to flow, and that's going to be really important for when we're extruding. And then the binder is actually just being used to hold the part together during the printing process. So the first step of the printing process is simply to print. So we're extruding this paste. It's viscous enough that it can simply just be pumped through this needle that you're seeing here. It's very flowable. Of course, there's no loose metal powder because all that metal powder is encapsulated in the solvent and the binder. So the first step of the printing process is exactly like you see here. We're simply printing and we're using that solvent to flow the material through the needle. After a layer is printed, it's then dried. This is just done with heat. And here we're actually removing the solvent out of the paste, out of the material. So we're drying up that layer. We're going from kind of a toothpaste kind of to like a foam-like material where we're removing that solvent. We're raising the green body density and leaving behind just solvent, just binder and metal powder. The next step here is to actually machine or to shape. So this is actually a machining step that's happening every single layer where we're now going through and refining with traditional machining operations, where we're cutting the material, we are refining the shape, we were overprinting a little bit, and then we're coming and trimming it back to really hone in the part. Which is why I don't know if you've ever seen a Mantle part before. I don't know how well it'll come across on my camera here, but the surface finish is really just exceptional because we're getting that from the machining process. The features are very, very sharp because we're getting that from the machining process, where we're just kind of putting this paste where it needs to go, and then we're coming back and refining that shape with traditional CNC cutting tools. So this is going to happen every single layer, which is why we can do these really, really deep ribs and things like that, because we're going to print, dry, machine over and over and over again to build up a part. After a part has been produced in the printer, it's going to go into a furnace. If you're familiar with metal injection molding or powdered metal processes, this is a sintering step. The part shrinks about 9% in the furnace, which is a lot less than most powdered metal processes, but it does shrink about 9% here. And that's the steel actually densifying and bonding together, where we're removing all the binder out of the part. There's no binder left in the part after this process. And the result is a dense, strong metal part with isotropic material properties and no residual stresses. So it's very, very stable. I have a quick video here just because it's a little bit of a unique process. You can see starting with that metal paste that you're seeing there, we're sliding in that dough plate that we're going to print on top of, just extruding out that paste material where we're printing a layer of that paste. You can see it being dried, that layer, and then it goes ahead and is machined. And again, this is happening. Every single layer is a print, dry, machine, print, dry, machine. That happens every single layer to refine the shape. It also enables us to use some really, really small cutting tools because the force on the tool is very, very low because it's a layer at a time, which allows us to do some, the smallest cutting tool we're using today is a 6 thou ball and mill. You can see it's then placed inside of a furnace. That furnace is going to take anywhere from 24 to 42 hours, depending on the size of the part. And then what comes out is a dense, strong tool steel component. So hopefully that helps understand the process a little bit. It's a very unique process where we're printing, drying, and machining every single layer. It's great to have, a very fancy print process. There's a lot of people out there who have these fancy print processes, but what actually matters is that it's saving our customers time and money. Just a couple of examples here that we're not going to spend too much time on, but I have a bunch of other ones that we will go into of some threaded inserts where all those threads were left as printed. You know how difficult those would be making in an H13 insert, would require extensive sinker EDM. All of that was left as printed, molded those fluid fittings at 50% less time. A good component here for a consumer dishwasher component, 67% less costs, 71% less time. And then this very, very common to talk about metal 3D printing and molding with conformal cooling. An example of an automotive optic component where 50% cycle time reduction thanks to conformal cooling. And they were actually able to achieve an A1 polish, which if you know about optic molding, the finish of the mold is very, very important to get that very clear finish, which they were able to do off of the Mantle insert. In terms of materials, very commonly asked, we print some industry standard tool steels, H13, which is commonly known as really the workhorse of injection mold steels. Comes out of the furnace at about 42 Rockwell as sintered. And if you wanted to afterwards, you could go ahead and heat treat that up to over 50. A more newer material for us is 420 stainless steel. This was a result of feedback from mostly our medical device customers who really wanted a corrosion resistant tooling material. It's ideal for those applications, and another great, very common tool steel. One of the most common questions we get is asking about the durability of the material. Earlier we were talking a lot about prototyping, about product development, and they ask of, is this material durable? Is it just for prototyping? Is it just for 1,000 shots or 5,000 shots? And just quickly, this is not necessarily an example that's overly related to product development, but just to show the durability of the material. An example with Tessie Plastics here, where they've molded over 3.4 million cycles and counting, and have seen no unexpected signs of wear on the printed tool. I actually have this tool with me here today, and this is a good example. Actually, this is a 32 cavity tool that they're running. These are sticks for your deodorant, that are the screws that advance your deodorant up through the tube. They have a 32 cavity tool running these. They've replaced 2 of them with Mantle printed inserts, and these have been running for, I think, over 3.5 years now. 3.4 million cycles, 6.8 million parts plus, because there's 2 of these running, and they haven't seen any signs. So very much can be used for a prototyping application, but also very much can be used for production applications as well. Just one more quick, a little bit more about the process before we start diving into a bunch of the application examples. People are always asking is it compatible with standard operating procedures? Can I mill it, grind it, machine it, wire it, polish it, texture it, weld it? All of that's possible because certainly there are applications where you're going to need beyond the tolerances or surface finish that are possible with our technology. And all of that can be done, often still removing much of the time and cost of the process, because we're getting you 75% of the way there. Awesome. At this point, going to jump into a bunch of examples of how companies are actually using this technology specifically for product development and accelerating product development. We're going to look at Hypertherm, Heiko, a medical device OEM who unfortunately I can't name who they are, but have done some great work with Mantle, Westminster Tool, and Nicolay Plastics, which are a little bit unique in that one's a tool maker and one's a molder. But we'll look at some OEMs first to understand how they're using this. Starting with Hypertherm. So Hypertherm is a leader in these plasma cutting and plasma torches components. This here is a component that's used as a shield cap for a cutting torch, which I think actually holds the consumable in the torch. They had a new design coming out where they needed to very, very quickly validate this design, because I'm sure you can imagine a plasma torch gets very, very hot. So there was some pretty unique material requirements for this cap. This was being molded in a 30% glass-filled peak. So the melt temperature on that was 720 degrees Fahrenheit, and they were actually heating the tool here to 355 degrees Fahrenheit to improve the moldability of this peak material. So very, very abrasive, very, very high temperature material. This is actually a slide component that's used to form the outside of that cap. They printed in an H13 tool steel, about 129-hour print, so about a week of printing. Of course, that's a little less than a week. Of course, that's fully unattended, so all that time is just the printer kind of working on its own. They did have to do a little bit of finishing here. They wire EDM to taper, and they just ground the outside of it to fit into the mold base. All in all, it took them just 2 weeks to go from the tool design to actually running this in the press. You can see the part actually installed in the press here around the core component where it's forming the outside of that tool, and they were able to do this with a 75% lead time reduction, 75 cost production. And the reason for that was because they used all of the printed detail with no processing to that part detail. So where the mold is actually touching plastic, all of that was left as printed. And they were running that 30% glass full peak. So that high temperature, high abrasive engineering resin with no real challenges here. You can see it actually being run here. You can watch videos like this all day, but you can see no challenges here. And they produced, a couple thousand of these parts, I believe, with no challenges. So all in all, what did that mean? It meant they reduced the lead time on this from 8 weeks down to 2 weeks. And you can imagine how significant that 6 weeks, month and a half of time savings is when they're trying to validate this design to move to production to get this part and get this design on the shelves, on the market, and being sold. The reason that they were able to save so much time and cost here was because, like we mentioned, they cut out all of the EDM time that would have been involved. If you look at the ribs on this component, all of these ribs in here would have required electrode burning, which is very expensive and very time consuming. They're able to remove all of that out. They still did a little bit of wire EDM just for the taper on the slide, and then the grinding components, but still from 8 weeks down to just 2 weeks, thanks to their use of Mantle. So allowed them to do that critical testing and manufacturing validation much earlier in the process because they weren't waiting on tools to come in. The next is Heiko products. They are a component manufacturer located down in New Jersey. They make a lot of wiring components, harness components, clips, and different electrical components. You'll see some examples here. Just a quick quote from their VP of Operations before we start looking at some of their examples. But using their Mantle technology, they've already brought up a new product to market 2 months faster than they would have otherwise. So really good results from Heiko here. You can see some of those plastic components behind there, but we'll talk about some of them here. The first example here, this is a wire management, wire routing component. This is a new design that they were bringing to market. This was being molded in nylon 6/6, so not an overly abrasive material here. They went ahead and printed these inserts in H13 tool steel. To conventionally produce these inserts, they would have had to have done these following steps. They would have had to rough mill it first, designed, programmed, and machined electrodes, which again, EDMs are a pretty common theme for us today. They would have squared the blocks afterwards, drilled and tapped the holes, done the actual burning process for that feature detail, wired the ejector pin components, and then burned in the gates. Using their Mantle machine, they removed all of that EDM out. They had to do, of course, the printing and sintering. They still squared up the inserts. They tapped the holes on the back to hold it inside of that mold frame. They wired the ejector pins and burned the gates. But the real benefit here came from the ability to leave the cavity detail as printed. So they didn't have to touch any of that feature detail where the plastic's actually touching the steel. Key results here, passed all the form and function that they were anticipating, which allowed them to produce these parts and start selling them. They've run this over 750,000 cycles, over 3 million parts with no issues. They saved 2 weeks on this tool, so 2 weeks faster in getting this product to market, and 60% of the cost compared to producing this tool traditionally. So saved a lot of cost as well as time here. They actually had such great success here that they printed an entire duplicate of the insert to double the cavitation because there was so much demand for this product. And of course, huge benefits there in being able to meet that demand faster because they're able to produce that tooling so quickly. Another good example here. This is a new product design that they're bringing to market for a threaded component. I think I show it here on the next slide. They found out that they were going to need to make a change to the external threading. So they needed to mold some new parts because they weren't going to be able to validate that threading with a plastic component before moving into production. So they very quickly needed to produce an insert to understand how the threading was going to perform. They did this in H13 tool steel. They printed the insert in 2 days and only required 3 to 4 hours of their toolmaker time, which is another common theme we could talk a lot about, but is how valuable toolmakers' time is and how hard it is to find toolmakers. So not having to tie up their toolmakers who were busy working on other things, but only required 3 or 4 hours for them to square and tap the holes here. You can see there's the actual plastic component there. The threads were very crisp. They blasted them afterwards, but they didn't do any other finishing to the mold detail. So they didn't have to do any EDM or anything like that to get those threads to work. They were fully functional MPT threads. They gauged and sealed properly, and they saved over 2 weeks by doing this. So just a good example of a prototype tool here where they needed to validate something very quickly. We're able to do that by using some steel tools here. A little bit of a unique example that is not as related to injection molding or plastic parts here, but I thought it was worth including. This is a copper crimp component that's used for crushing copper termination tool here. This was again needed for new product development. They designed it to fit into an existing die base so they could test this very quickly. And what was so cool here was that it didn't actually tie up any of the resources from the tool room to produce this. And it kind of allowed the engineering team and the product development team to be their own tool maker. They didn't have to, wait for anything. They were able to just throw it on the printer, use them as printed, and help them dramatically reduce the time to get this to market because they understood how it was going to crimp, how these tools were going to work much earlier on without having to go to the tool room, wait, and tie up their tool room time. One last example here from Heiko before we move on to talking about some other medical examples. This is a consumer product that they were prototyping for a customer. As you can see on this tool here, would have required really extensive sinker EDM, multiple electrodes to produce these very deep, thin ribs that you're seeing on the tool. It also had a parting line at 15 degrees, which makes it additionally challenging to produce. They printed these inserts with Mantle. You can see the actual part there on the right, all of those ribs that were able to be molded off the printed tool. And they estimated they saved 40 to 60 hours of sinker EDM time by doing this and required very minimal finishing after printing. They just squared the inserts and then tapped the Moving over to some medical device applications. This comes from one of our customers, a leading medical device OEM who has a few of our machines. And this is a prototyping tool for a medical component they were bringing to market. Here, they were looking to test both acetal and radel in the prototyping stage to understand which material was going to work. Both are pretty abrasive engineering resins, so are difficult to work with. Radel molds at 38,000 psi and has a high melt temperature. Acetal actually emits a corrosive gas during molding. So both of these mean that it's very difficult to use an aluminum tool or use a plastic 3D printed tool during that. They also, of course, needed to use production materials here, acetal and radel, because they were doing not just prototyping, but also some trials and FDA work to understand how these parts were going to perform. Example here, printed these in 62 hours, about a day and a half in the furnace, finishing about 24 hours on these inserts. That was adding the ejector pins, tapping the mounting holes, and just grinding it to fit into the mold base. So pretty consistent finishing required for these inserts, but ultimately it was mold inserts in just 8 calendar days. They estimate, so 122 hours of fabrication, but only 24 hours of active hours, which is obviously very important to save their toolmaker time here. So tool steel molds in just 8 calendar days here. That was a reduction from the estimated 7 weeks they would have had to go out of house here because of how much secret EDM it would have been required to build those thin ribs on this component. And the amount of active hours required went down from 148 hours down to 24. They also saw a 50% cost reduction. We haven't talked too much about tolerances today, but the entire tool was accurate within 1 thou as printed, which meant they didn't have to do any additional finishing, and all the molding surfaces were left as printed as a D2 finish, which is like similar to a Synchro EDM matte finish, which was totally fine for this application. So, and all the molded parts passed all visual and dimensional requirements. So, good example here of really, really dramatic reduction in lead time on a medical prototype tool, dramatic cost reduction, thanks to being able to leave all that feature detail as printed, not have to go through that Synchro EDM process. A quick look at how the actual steps, again, very common themes here, but removing most of those very, very expensive and time consuming processes from the tool building process, specifically all of that Synchro EDM time to reduce the lead time from 7 weeks down to just 8 weeks. Looking a little bit differently here at one of our customers who is a tool maker here, Westminster Tool, but they work with a lot of medical companies, medical OEMs. They have one of our machines here, and they recently used the technology specifically for helping a large medical OEM bring a new medical device product to market. The customer here needed to produce what they call production representative parts as soon as possible. So the parts needed to be equivalent to what was going to be produced in production, which meant they needed to be molded, and they needed to be molded out of tool steel. They were doing this to both validate the part function. They wanted to understand the molding processor parameters to save them on the back end. And here they were doing some material selection through biocompatibility testing as well. So they wanted to test a couple of different materials here to understand how they would perform. The part was incredibly complex. This is actually just an example, a similar looking part as the part is confidential here, but it's a very, very complex part. Requires very, very complex mold tooling to produce them. And there's 40 swipe by shutoffs on this tool, as well as a contoured parting line. So it was an incredibly challenging part for them, which is why they turned to their Mantle machine here. What the steps involved to produce this with Mantle, there were 6 days of printing. That's to produce both of the inserts, which we'll look at on the next slide here. Of course, all that printing was done unattended, so a total of less than 2 hours of active time from the Westminster Tool team. They sintered the inserts, so again, unattended, but about a day and a half in the furnace. And then they did about 2.5 weeks of finishing here, or 55 hours of finishing, which accounted for squaring of the blocks, hard milling the primary vents for gassing, wire EDM of the ejector pinholes. They tapped the water lines and bolt holes. And they hard milled just a few of the difficult swipe by shutoff areas. The result here, they were able to mold production representative plastic parts in just 4 weeks. This was a reduction in lead time of 50% from 8 weeks down to just 4 weeks, which enabled their medical device OEM to test and validate this part much faster than they would have traditionally. They also saved 65% of the traditional manufacturing time, which allowed their tool makers to be working on other things while the Mantle machine was taking a lot of the work off their plate. They molded over 7,000 different pieces across both ABS and a polycarbonate ABS blend here to understand which material they wanted to proceed forward to in production. So a good example here of a medical prototype tool used in tool steel reduced the lead time by 50%, 8 weeks down to just 4 weeks to be actually trying injection molded prototype tools. Lastly, we're going to look at some examples from nickel plastics. Again, they're an injection molder, so a little bit different here, but they're using the technology to really enable their customers to rapidly prototype plastic parts to get to market faster. Nickel Plastics often says that the Mantle machine allows them to produce production tooling and prototype timing, which enables them to use production quality tools during the prototyping stage. The printed inserts are anywhere from 75 to 95% complete. This is one of their slides that I'm using here. Inserts generally just require refining of ejector pinholes and tapping of water lines, very similar to what we've looked at before. This allows them to dramatically reduce tooling lead times. They can produce steel tooling as little as a week, which is a huge opportunity for their customers, as well as for people that are looking to prototype. It also frees up their internal tool makers to work on other critical projects. Example that I have here for us to talk about is this component that I actually have this one on my desk. It's my favorite tool, so I'm always using this example. This is a component for their customer, Gamber Johnson. This is what the component actually does is it's a slam latch, which I guess is used for holding tablets or computers to the dashboard of emergency vehicles, of an ambulance, of a police car. When you see a police officer going down the highway at 80 miles an hour typing on their computer, they're using this component to help hold that laptop on the dashboard. One thing that's really, really important here for Gamber Johnson is that first to market is incredibly important in the accessory industry. This is true for phone cases, for tablet holders, etc. And that the first person to market often captures the majority of the market share. So bringing this product to market quickly was incredibly important to them. They wanted to be the first one to offer this when a new tablet comes out, a new laptop, a new phone design, etc. So they went to Nickel Plastics knowing they had this technology to hopefully allow them to produce tooling much faster than they would have traditionally. The part's quite complex here. It has some very steeply angled faces, some thin ribs. Again, this common theme of would have required quite significant sinker EDM time to produce these molds traditionally. And they estimated it was going to take them up to 6 weeks to fabricate these traditionally. You can see there's actually 3 inserts that were printed here. There's another insert that drops inside of the insert up top. You can see I have one of the inserts on my desk here with me today. They used Mantle to print these in H13 tool steel, printed in about a week, went in the furnace for about a day and a half. Total, that was just 10 hours of finishing afterwards, which again, common theme here. They wire EDM the ejector pins. They did just a little bit of grinding to ensure the inserts fit well into the mold base and there wasn't any unnecessary flash or misalignment. You can see that the tool is actually in the mold here, and ultimately that enabled a lead time reduction from 6 weeks down to just 2 weeks. They estimated the amount of active time for their tool makers to produce this down from 180 hours down to just 12 hours. And this was molding a 35% glass filled nylon, so a pretty abrasive material they really benefited from the tool steel here with that high quickness. Looking at the steps again, really just removed most of the very, very costly and time-consuming steps of the process. All that EDM was taken out and allowed them to get to from 180 hours down to 12, lead time from 6 weeks down to just 2 weeks. Going to wrap up here. Thank you, and I'm certainly happy to take any questions that anyone has. But just a quick benefit here, or quick summary here. We really see our customers the benefit of using steel tooling early in the development phase. This now enables you to get these end-use plastic materials and manufacturing processes for these production parts during the prototyping step. Enables part certification and trials. You're not just validating the part design, but now we're actually validating the production manufacturing method, the mold functionality, the molding parameters, the molding dimensions, etc. Of course, we see customers that use steel tools for prototyping, and then ultimately just run them in production as well, because it is steel, like we looked at, so it can be used for millions of cycles. It ultimately allows you to de-risk production and bring products to market faster, more affordably, and with less risk. Thank you for giving me 40 minutes out of your day already. Happy to stick around and answer some questions. Hopefully this was valuable for you. I'll say if you have any questions, feedback, or thoughts, feel free to send me an email. Also happy to take a look at any of your molds if you want to understand, would it be a good fit to print? How much would it cost? How long would it take, etc. Always happy to take a look at some of your inserts and talk to you. I always learn lots from those conversations. So feel free to reach out if anything comes up. And thanks again for joining us.
All right, we do have a couple of questions in the Q&A. Again, that is still open, so please send them in if you have them. This question, they're asking about the part you showed in your hand, and I think they're referring to the Tessie Plastics insert
Sure.
from earlier. Do you know the time breakdown for printing, drying, and finishing on that one?
Yeah, so I don't know the exact time breakdown of each of those steps, but I can speak to that a little bit. And that an insert like this would take about 24 to 32 hours to print. And the actual most time-consuming part of our process is the drying step, actually, in that we can print material very quickly. We're not getting feature resolution from printing, so we're able to extrude quite quickly out of a relatively large nozzle because we're going to come back and clean that up. But ensuring that all of that solvent is removed from the layer and that the layer is the right density and firmness for machining is really, really critical. So a layer can take a few minutes to dry when it could take just, less than that to print or machine. That is one reason actually that we see some really good economies of scale of printing multiple parts at once, because the drying time does not increase with more parts on a build plate, because the lamp comes over the entire build. So it may take you 24 hours to print one of these, but you could do two in 30 hours. So a lot of our customers are printing a lot of parts at once to take advantage of that.
A couple more questions just about the printing process.
Sure.
As the machine is building up each printed layer, is it milling every layer that it's printing?
Yeah, so I did oversimplify it a little bit here just for the presentation, but every single layer is milled flat, and that's just done with end mills where every layer is printed, dried, and then milled flat. After every 10 layers or five, depending on the feature resolution, that's when contour milling is done with ball end mills. The smallest end mill is going to be a 6 thou ball end mill, so giving you very, very sharp, crisp features. And that's going to happen every 5 or 10 layers. So there is milling being done every layer, which is just milling the layer flat. And then every 5 or 10 layers, we're contour milling features and the outside of the part to improve surface finish and things like that.
All right. Okay, so question about conformal cooling. Can you do conformal cooling with horizontal bores? And they're asking, I think, about support structures here.
Yeah, so we absolutely can print horizontal bores. We do recommend a teardrop shape depending on the size of the bore itself, of the hole itself, and we have some design guides that we can give that, because obviously we don't have a support material, so there is some droop. The paste, luckily, is quite viscous, so it does hold in place quite well. So we can print fairly large holes without that teardrop shape. But often our customers are doing that teardrop shape. They're undersizing the inlets and outlets and just drilling those afterwards to add the tactin. So we can do that. It just depends on, we often do that teardrop shape to self-support so it doesn't droop too much.
All right, another one about the process. What is the layer thickness?
Yeah, so our layer thickness is about 150 microns, but we mill it back to 100 every single layer. This is a common question we get, and I think it's important to know that we do not get our feature resolution from layer thickness or from nozzle size like other FDM style printers or extrusion style printers do. We actually think we should have a bigger layer thickness, because that means we can print faster, because we're going to come through and clean it up anyways. So today it's about 150 microns milled back to 100, but it doesn't define our resolution, because we're going to come through with tiny cutting tools and add get that part to exactly what you want it to be.
Yeah, you're kind of, in a way, you're a little bit consolidating like what might be a post-process step with a different type of printer. You're doing a lot of that shaping.
Yeah, I think what's important to know too is that shaping is being done in a very soft state, where there are other metal 3D printing technologies that do a hybrid approach, but they're often using a laser to harden metal and then coming through after machining it. Our material is still a paste at that stage because it hasn't gone into the furnace yet, which enables us to use really small cutting tools, machine really, really quickly, things like that you would never be able to do on a hardened tool steel, because it would just be too challenging to machine.
All right. Post-processing question. Is it necessary to grind the insert parting surface?
Yeah, so I think the answer to that is it depends. It depends on what's an acceptable amount of flash. It depends on the geometry. It depends on, is it a class 101 medical tool that's going to, go in someone's body, or is it a prototype for something that's going to sit on your desk? And it really just depends on the application. We see our customers running inserts completely unfinished because it's like, we need 1,000 prototypes. We need to do that at Tool Steel. Great. We see customers that are touching every face because it's a really important medical tool or something like that. So it just depends on the part, the application, and what's an acceptable amount of flash. I don't know, this won't come across well, but I have an example here of, this is a part molded with Mantle, and you can see that kind of matte finish, and that's with no finishing done to the actual cavities.
A question about the ejection pin holes.
Sure.
Why is it necessary to wire EDM them? Why not get the holes through the Mantle process and ream them?
Yeah, so I will say that that's absolutely an option as well. Most of our customers, if they have wire EDM, they prefer it. So they'll print a pilot hole with Mantle, and then they'll drop the wire through and quickly just wire the hole. If you wanted to ream it instead, absolutely, you could do that. Whether you print a pilot hole or just ream it completely afterwards, absolutely is an option. You can print that starter hole and finish it however you want. But as you know, if you know ejector pins, they're plus or minus nothing usually, so that's a little bit outside of the tolerances, the capabilities. So generally, they require a little bit of finishing.
Can you talk a little bit about the cost of some of the parts that you showed?
Yeah, absolutely. So as you know, if you're in the additive space, there's a lot that contributes to a part cost. It's not just the material, it's consumables, it's other consumables, it's amortization, it's labor, everything like that. An insert like this would cost you $1,000 to $1,200, and that's really before finishing being done to it. So for a tool steel insert, we often find that's quite competitive with traditional methods, and of course, there's that speed advantage here. If you're interested in exploring more costing, you have some good content I'm happy to send to you, as well as happy to run ROI analysis and costing on your parts or your tools to give you a better understanding of what they would cost and the time involved. But generally, seeing something around this size or baseball or softball size being around $1,000 to $1,500, depending on the exact geometry, of course.
What is the CAM program required to run the system?
Yeah, that's a great question. We didn't get too much into software today, but Mantle has a software that controls the machine, and it automates all of the CAM process for you, because we are machining, so there is tool paths involved, and our slicer and our software does all the tool pathing for you, both additive and subtractive. So all you have to do is upload your step file or your STL file, and it's going to take care of the rest for you. So we're removing that CAM step from the process, which we often hear is a good thing, because hiring someone who knows how to do CAM or training CAM is a lot more challenging than I think I could teach anyone on this call how to print something like this in an hour or two, which is pretty incredible, because you'd imagine how long it would take to build this, to learn how to build something like that traditionally. So our software takes care of all the CAM for you.
Question about materials here. Are H13 and 420 the only materials offered? Yeah.
Yeah. So today, H13 and 420 are our two materials. We've received really good feedback about those two materials, and that they cover a wide variety of what's used in the molding industry. H13 for the high hardness, as well as the 420 for the corrosion resistance. Our next material, we're looking at going to something harder. We often or occasionally get requests for something like a D2 or an A2 or an even harder material. That may also open up some applications in progressive die or stamping or even some die casting or MIM applications as well. So today, just for H13 and 420, but the good thing about this process is anything that can be sintered can really be printed and used in our process. Of course, there's a lot of tweaking in our material. I shouldn't make it sound that simple. Our material science team wouldn't be happy with me, but there's a lot of work going in to validate the material. But there's a lot of materials and things we can do with this technology that we will do in the future.
Is it fairly simple to switch materials if you wanted to go from one to the other?
Yeah, it's as simple as replacing that paste tube and doing some purging and replacing that needle, which is a relatively low cost part anyways, that it's not worth risking the contamination. So it's less than, I think it's less than 30 or 40 minutes to swap materials, which is pretty good.
Two questions here. What's the max part size?
Yeah, great. So the build of the printer itself is 200 by 200 by 150 millimeters, or 8 by 8 by 6 inches. So theoretically, that's the maximum part you could print. Of course, there's a little bit of shrinkage in the furnace, so the maximum part's going to be 8% or 9% less than that. But we see a really good size for us in the 4 or 5 inch range and smaller. The reason for that is because, additive, or at least additive like we do, part times get exponentially longer, costs get exponentially longer the bigger you get. So we reach a point where we aren't competitive with traditional, and we're the first to admit that. It just depends on the application, the part, whether they're using conformal or not. But we see inserts kind of in this size range that are medium to high complexity as kind of a slam dunk for us. So again, long-winded answer. The biggest part you could do is 8 by 8 by 6. We see the most value in kind of the 4, 5, 6 inch range and smaller.
Yeah. What is the rough cost of the system, the printer and the furnace together?
Yeah, rough cost of the system is about 400,000, depending on a couple things, or installation, shipping, and things like that. So you're about $400,000 all in. So pretty competitive with high-end CNC or Synchro EDM equipment. It allows you to get up and running really, really quickly and easily.
All right. Question about the sintering process. Does the post-processing heat treatment to increase hardness keep the tolerances obtained from the printer?
Yeah, so in the printer, we're able to achieve CNC tolerances, right? Because we are essentially CNC machining. In the furnace, that is where we're going to lose our tolerances. I should have had this on a slide somewhere, and I regret it, but our tolerances are going to be plus or minus a thou per inch. So on a 3-inch part, you're going to be plus or minus 3 thou. And that's a result of the sintering process, in that how closely can we predict that 9% shrink to understand where the part's going to end up afterwards. And that's why that plus or minus a thou scales with size, because predicting plus or minus a thou on a 5-inch part versus a 2-inch part is a little bit hard to understand, or harder to do. So our tolerance is plus or minus a thou per inch, and that is a result of the sintering process, where we're predicting how much that part's going to shrink.
Can you polish the material?
Yeah, absolutely. So that's one thing that's really, really important with molds is that they can be polished. The result of molding right off of our material is going to be, I don't know how well this comes across, but kind of a matte D2 finish, very similar to a Synchro EDM finish, which is great for a lot of applications. If you need to polish more, you can get it all the way up to an A2, or we've even seen beyond that to get that really, really shiny finish, or the optical finishes that are required. So you can absolutely polish it using traditional polishing methods. No problem.
All right. Taking a look at our question list here. What is the cost of the material?
Yeah, so we sell material in tubes of paste, which are these 8.8 liter tubes of paste, which is probably a little bit complicated to understand, but a 0.8 liter tube of paste costs $625. But I would say that an insert like this is going to take half to 3/4 of a tube of paste. So a part like this would be $200 to $300 worth of material, and then of course all the other things that are baked into a part cost. But again, long-winded answer to say that a tube of paste costs $625, but that's a little tricky. So a part like this would be about $200 to $300 of just material.
Gotcha. All right, the questions are still coming in.
Yeah, no problem. I'm happy to. I'll be here all day.
Does Mantle offer printing as a service, or only selling machines?
Yeah, so we only sell machines, and the reason for that is because our customers obviously have purchased machines to sell parts, and we don't want to compete with our customers. The caveat to that I'll say is that during an evaluation process, people come to us all the time and they say, I want to understand what my part's going to cost, how long it would take. I want to try it before I buy it. And that's a benchmarking process. We're more than happy to print parts for you as part of an evaluation. So in those situations, we would print parts for you at cost if you're interested in understanding the value of a machine for your organization. Otherwise, we'd obviously, of course, love to refer you to one of our customers who has bought machines for that purpose.
All right. A couple questions in here that I think are going to be better for follow-up afterwards.
Yeah, no worries. If we didn't get to your question, either shoot me a quick email, or I'll look through probably tomorrow and respond to any questions we didn't get to. But Thanks again for coming, everyone, and thanks, Stephanie, for hosting, and for AM for hosting, of course.
Yeah, thank you, Mantle, for making this possible. Again, you should get the recording in your email in the next 24 hours. It's usually a little bit faster than that. Thanks everybody for listening in and joining us today.